Okay, so I think we can start. Today I would like to tell you about our recent endeavor into second virial coefficient of helium with new potential our team developed. The problem seems a bit simple maybe, but there are several quirks that I find quite interesting, and I would like to share them with you. So let's start with the virial equation of state. These B and C virial coefficients obviously describe the deviations of the real system with respect to the ideal gas law. We are mainly interested here in the second virial coefficient B. As Michał Przybytek told, the density can be eliminated by using Clausius-Mosotty equation. We can arrive at equations dependent either on the refractive index or, as it's presented here, on relative electric permittivity. Using this form, we can utilize it in several fundamental metrology methods, such as the name suggests, dielectric constant gas thermometry or refractive index gas thermometry, and several others. As Michał Przybytek also said, it can be used to look for new pressure standards, but obviously to do so, we need quite accurate values of at least B and B epsilon. It would be ideal to have C, but it's for the future, maybe. So how to arrive at this thermodynamical or quantum or statistical mechanical quantities? As quantum chemists, we obviously start from the Schrödinger equation. We usually factorize it to the electrical and nuclear parts. Solve for the electrical part using the frozen nuclei Hamiltonian, and then use it further to solve for the nuclear part. At the most crude Bornheimer level, this interatomic potential is just this epsilon r from the electronic part. What's quite notable here, in this equation we can legally have only mu n, which is reduced to nuclear mass. However, if you look in the literature on similar calculations as the one I present, people use here reduced atomic masses. It's quite illegal, but effective because it improves the results. I can show you why in a minute. So our interatomic potential includes adiabatic, non-adiabatic, relativistic, and leading QED corrections, which can be described, for example, according to non-relativistic QED theory, which was described, for example, by Mariusz Puchalski in his talk. Also, we make sure the long-range asymptotics of the potential are correctly described by Casimir-Porler theory. This potential actually builds on the 2017 potential by Michał Przybytek et al. It improves the components, recalculates them, so it's maybe nothing new physically, but we improved the potential, the reliability of it. So I told you about these nuclear masses and how they are replaced by atomics. To observe why, we can use the so-called non-adiabatic perturbation theory, which acknowledges that apart from this factorized electronic nuclear part of the wave function, we have also non-adiabatic correction. We can iterate it and obtain more and more accurate equations for the nuclear part. Here you can see that this improved equation contains this first order term, which will be interesting for the numerical point of view, but most notably it includes distance-dependent masses, effective nuclear masses. It's quite interesting that they tend to, obviously, on this electronic mass to the nuclear mass to the second power level of correction, they tend to atomic masses, and for helium they do so very rapidly. Even for very small r, these quantities are very similar to reduced atomic masses, which validates this practice of solving this simple equation, but with masses replaced. Okay, so how to go from these quantum chemistry calculations to thermodynamics? We can describe this second virial coefficient in terms of the partition functions. Partition function can be either expanded classically, which is a kind of very simple formula, or we are interested more in quantum forms. It's basically a sum over states, but for the bound states, it's quite simple, especially for helium, which for helium-4 has only one very weakly bound state, and for helium-3 there are no bound states. However, for the positive part of the spectrum, it turns into integral over energy, and we also need the state density there. State density, as shown by, for example, by Kilpatrick, or I think earlier by, I can't remember now, can be related to phase shifts. So we need to calculate phase shifts quite accurately. We do so using this kind of formula. We assume that, or we observe that as the interatomic distance goes to infinity, the atoms obviously behave more and more like free particles. So from this formula, we can calculate the apparent shift for any given distance, and for the infinite distance, it should approach the true value of the phase shift. As you can see here, we actually don't need the wave function to calculate the phase shift, but the logarithmic derivative of it. So we basically don't need the normalization of wave function, which will be kind of useful. We use normalized Nonaromatic method, but first, to use Nonaromatic method, we have to get rid of this pesky first derivative. There is a clever trick proposed by Leroy and Wallace. They transform the function for which we solve with this kind of formula, and we arrive at the Nonaromatic tractable form of the equation, which has more complicated this linear term, but it's doable. Typical Nonaromatic recurrence is kind of simple, well-known formula. Renormalized Nonaromatic switches this three-term recurrence for the two-term one, for the cost of forfeiting the normalization of the wave function, which we, as stated before, we don't need anyway. So it's kind of perfect for our application, and it has an added benefit of not the propagated quantity does not explode in the classically forbidden regions, which is kind of useful too. There's obviously several pitfalls. For example, the phase shift generally is defined only modulo pi. So for our calculations, we need to assume some convention of scaling it. We assume that shift is 0 for a free particle, and when we propagate, we make sure that the shift is continuous when the potential changes during propagation. And also we have to sum over all possible quantum or possible momenta, but we can assess when we can basically stop this calculation by so-called Born approximation, not Born parameter, but Born approximation, which shows us how this shift should decay. Okay, so as for results, this is the phase, the sum over all shifts multiplied by 2L plus 1. So it's basically a sum of a function of phase shifts for helium-4. There is a theorem called Levinson's theorem, which states that for 0 energy, the shift should approach n pi when n is the number of bound states for the certain potential. We observed so for helium-4, and also in calculations for helium-3, we see that this potential goes to 0. Helium-3 does not have any bound states. Helium-4 has 1, so it looks reassuring. Okay, so these are results compared to the.
Paweł, 1 minute left.
Okay, so, yeah, I'm finishing. These are our current results compared to for helium-4 compared to the previous ones from 2012 by Sensek et al. And we basically corroborate those results with significantly reduced uncertainty. And what's also interesting, we can see, as our colleagues Bogao and Louis Pitre suggested, that these sigmas from 2012 were too conservative, and indeed, even in terms of these previous uncertainties, we see that our results are consistent. Actually, this month there was a paper by Bosong, which also performed the same calculations, but with previous potential of Michał Przybytek from 2017, and we are basically completely in complete agreement for helium-4. There are massive disagreements for helium-3, but it's a topic for longer discussion. We believe that our results are the proper ones, and they agree also with Sensek. And also there is a graph with various components of the potential: relativistic, adiabatic, Casimir-Polder retardation, and non-adiabatic components turn on or off, and how they affect the total virial coefficient. This non-adiabatic contribution is basically the difference between the fully non-adiabatic calculation as shown with this napped nuclear equation, and with this simplified form when nuclear mass is just replaced with atomic reduced mass in the equation, and we can see that they are way below sigma. So it's also another argument that this this quite illegal but effective practice that was observed in the literature. Okay, so to conclude, just we observed that although our new potential does not include new physical effects, it's much more accurate. We had some feedback from experimentalists that it will be very useful for them as well. And our paper has been submitted and also reviewed already. We are just writing response to the referees, so you can expect it soon with more results than I was able to show you. And thank you for your attention.
Okay, thank you very much, Paweł, for the interesting